All right. Hi, everyone. Let's do lab 6. Okay, so we are given the matrix A and it row reduces to the matrix R. So we're given the row reduced form. And the first thing that we want to do is find a basis for the column space from the columns of A. Well, that's actually really straightforward because when I look at R, I see that it is the first column, the second column, and the fifth column that gives me a pivot. So I just take the columns from A that are associated with the pivots from R. So for A here, my basis for the column space of A, basis for col A is just 1A, 1, negative 1, 2, 3, 0, 1, and 3, 2, 1, 2. So I haven't solved for A yet, so I'm just going to leave that as an A in that first vector. Now it asks me for the rank of A. Well, I know that rank is the dimension of the column space. So that's the number of vectors in a basis for the column space. Since I wrote my basis, I can see there are 3. There are 3 vectors there, but we also know that rank is just the number of pivots. There were 3 pivots, so rank is 3. Now there are 4 rows, so the column space is a subspace of R4. Subspace of R4, and this is because 4 rows. So remember, when we're looking at what the column space is a subspace of, we look at the number of rows. Now, you're not asked this, but we know that 3 vectors spans a rectangular prism. So basically what the column space is a rectangular prism in R4. Now, B is asking me to solve for A and B. So in order to do this, we are going to write the non-basic columns, the columns that aren't basis vectors, in terms of the basic columns. So I have 3 columns here. I have column 3, column 4, and column 6. And I can write all of those as linear combinations of the other columns. However, it makes the most sense to start with this column right here, because that's the one that has an unknown in it. So I am going to write column 6 as a linear combination of columns 1, columns 2, and columns 5, the basis columns. And I know that I can do that. I don't have to do A. I don't have to go to A and row reduce. I can do that by just immediately setting up the row reduced form from R. So when I look at R, that's column 1, that's column 2, and that is column 5. And then I'm going to augment with column 6, the column that I'm looking for. So this is C1, C2, C5, C6 from R. And when we're writing linear combinations, we know that the answer gives us the weights for the linear combination. And that's kind of my goal here, is to write that linear combination. So this tells me then that C1 is equal to 5, C2 is equal to 0, and C3 is equal to 3. By using the basis vectors, we had something that was already in RREF, so we don't have to row reduce at all. So this tells me that 5 times 1A, 1, negative 1, plus 0 times 2, 3, 0, 1. So really, I don't even have to write that. That's not useful to me. Plus 3 times 3, 2, 1, 2 is equal to B, 1, 8, 1. All right. So now I know that these things have to be equal. What does it mean for vectors to be equal? For each of their components to be equal. So let's combine all these things on the left side. So I'm going to have 5 plus 9. That gives me 14. Then I will have 5A plus 6. Then 5 plus 3. That gives me an 8. And then negative 5 plus 6. That gives me a 1. So notice the last 2 components, the 8 and 1, they do indeed match up. Good news. If they didn't, that meant that would mean the row reduced form we were given was wrong. But so now I can easily solve for A and B, because I have 14 is equal to B, so B is equal to 14, and I have 5A plus 6 needs to be equal to that second component, which is 1. So my 5A plus 6 has to be 1, and my 14 has to be B. So then I end up with 5A is equal to -5 and A is equal to -1. So now I have A and I have B. Okay, so for my null space, the next question is to find a basis for the null space. So I know that for the null space, I can actually go straight to R. I actually don't even need to know what the original matrix is to find a basis for the null space, because what I'm doing is I'm pretending that R is augmented with zeros, and I'm just writing out what the solution set would look like. So here I'm gonna have 3 free variables. So I'm gonna call them T, R, and S. And I'm gonna write out my infinite solutions. So I'm gonna say that x1 is gonna be equal to -t minus 5s. x2 is minus 5t minus 6r. x3 is equal to t, and I'm gonna have to go down here. x4 is equal to r. It's also a free variable. x5 is not a free variable, and we can see that it is -3s. And x6, that's a free variable again, so that is s. So this right here is the equation of my null space. And now to find a basis for a null space, I just need to think of it as a vector equation. I'm not gonna rewrite it as a vector equation, I'm just gonna extract the vectors that I would use. So I'm gonna have a t vector, I'm gonna have an r vector, and I'm going to have an s vector. So my basis for the null space of A is equal to my t vector, so that's -1, 5, 1, 0, 0, 0. My r vector, 0, -6, 0, 1, 0, 0. And my s vector, -5, 0, 0, 0, -3, 1. So this right here is going to be my basis for the null space. Actually, let's square the basis for the column space up here, and the rank, and we know what it's a subspace of. So this is my basis for the null space, where this is just my t vector. It came from taking the coefficients of t in my parametric equation. This is my r vector, and this is my s vector, taking the coefficients of r and s respectively. Now the next thing that we're asked here is to find the nullity of A. So the nullity of A is going to be equal to 3. Again, we can think of that in 2 ways. One, there are 3 free variables. There are 3 columns without pivots. Nullity will always be equal to the number of columns without pivots. 2, well, we already wrote our basis for the null space here, and we see that it has 3 vectors in it. Nullity is the dimension of the null space. So it's the number of vectors in a basis for the null space. So our nullity is 3. Now, when I look at those basis vectors, they have 6 components. So the null space is a subspace of R6. And again, that's because those vectors in the null space, those basis vectors, have 6 components. But another way to think of this would be because there are 6 columns. So for the column space, we look at the rows, and for the null space, we look at the columns. So this is because 6 columns. All right, so we now have our basis for our column space and our basis for our null space, and we've solved for those unknowns. A was -1 and B was 14. And I'm just gonna remind myself of this down here. A is equal to -1 and B is equal to 14. By where we are reminded of the matrix with its row-reduced form. Okay, so for D, we want to know if the set of vectors A3, A5, A6 is linearly dependent or independent. Well, we know that dependent means column without a pivot, or it doesn't mean that, but that's the result of it. Column without pivot, and we know that if there's a pivot in every column, then they are independent. But we also already have the row reduced form. So I don't need to go take those columns from A and row reduce. I can just look at the columns from R. So here, if I look at the columns from R, I'm looking at the 3rd column. So that's 1, 5, 0, 0. The 5th column, 0, 0, 1, 0. and the sixth column 5030. Now this is on the way to row reduction, but we'll notice that it's not actually an REF, which means that I can't actually count my pivots from here. So we're going to have to row reduce a little bit more. We'll start by picking our pivot in the first column and making a 0. So I will do row 2 minus 5 row 1 to get 1 0 0 0 0 0 1 0 5 negative 5 3 0. And then we'll just flip those two columns, row 2 and row 3, and by two columns, I mean 2 rows. We'll flip those 2 rows, row 2 and row 3, to end up here, 1 0 0 0 0 1 0 0 5 3 negative 5 0. And notice that after those 2 row operations, we can see that we have a pivot in every single column. So we started by taking column 3, column 5, and column 6 from R. We row reduced a little bit because it wasn't an REF, and then we were able to see that there were 3 pivots. So the answer here is that these are linearly independent. Now for E, we're going to use R in a similar way. I want to write A6 as a linear combination of A3 and A5, or indicate that it's not possible. Well, I've actually already done the work. These vectors, A3, A5, and A6, are linearly independent. We saw that in D. So, oops, A3, A5, A6 is a linearly independent set. What that means is they all represent unique independent directions, and I can't get to any of them using the others. What does it mean that I can't get to any of them using the others? It means I can't write any of them as linear combinations of the others. So I cannot write A6 as a linear combination of A3 and A5. And if that's a little bit confusing to you, well, we could just go up here. We already finished that row reduction. That's what column 3 became. This is what column 5 became. And then I would augment with column 6 and notice that that contradiction does indeed occur there. Okay, so F now. Is it possible to find a basis for R4 from the vectors, from the column vectors of A? Well, to be a basis for R4, I need 4 linearly independent vectors to be a basis for R4. What that means is that I would need 4 pivots when I row reduce. But notice that a 4th row is a row of zeros. It's impossible to get 4 pivots. It's impossible to get 4 pivots because the column space has dimension 3. So I can't have any subset or subspace of the column space that would have dimension 4 because the dimension of the column space is 3, meaning the maximum number of pivots I could end up with is 3. So no, it is not possible to end up with a 4th pivot. So we need 4 linear independent, We need 4 linearly independent vectors to be a basis for R4, but rank of A is equal to 3, dimension of column space. So using the column vectors of A, we could get a max of 4 pivots. It is not possible. And by 4, I am sorry, I mean 3. I'm having a great day today, guys. A max of 3 pivots because the rank is 3. The dimension of the column space is 3. So it's not possible. And again, look, there are 3 pivots up there. It's not possible to like magically create a 4th pivot. All right, so G. Now G is using that last theorem we said that told us that the null space and the solution to AX equals B just differ by a point. So for G here, we are told that A times -104, -289 equals to B. What that tells me is -104, -289 is a solution, is a point on the solution to AX equals B. -104, what was it? -289 is a solution, or we could think of it as a point on the solution set to AX equals B. So to find the solution to AX equals B, we just add it to the null space. Okay, so what we're going to end up with is something that looks like this. x1, x2, x3, x4, x5, x6 is equal to my point, -104, -289, plus t times my first basis vector from the null space, -151,000, plus r, that's a really ugly bracket, plus r times my second vector from the null space, my second basis vector, so 0, -6, 0, 1, 0, 0. And then plus s times my last basis vector. So that is -5, 0, 0, 0, -3, 1. -5, 0, 0, 0, -3, 1. And this is my final answer. We just added a point to the null space. All right. Okay, so we have that A is a 14 by 10 matrix. That means it has 14 rows, 10 columns. Also, because probably we're going to be asked stuff about A transpose, we'll just note that A transpose is 10 by 14. Now, for A, we know that rank A equals 3, which means that there are 3 pivots. But we also know that there are 10 columns. So when we're asked what the nullity is, what we want to know is the number of free variables or columns without pivots. So here I can just do 10 minus 3 to get 7, and my answer is 7. Now, if rank A is equal to 0, in the same way, that means there are no pivots. So really, this is just the 0 matrix here. 0 pivots. And then we could say that means 10 minus 0 equals 10. So nullity of A is equal to 10. So in other words, we have 10 free variables. But we also know that the null space is a subspace of R10. A subspace of R10 because there are 10 columns. What does 10 vectors in R10 span? It spans R10. So we have that the null space is actually the whole space. Good. Now, if rank A equals 2, what is the nullity of A transpose? Well, another thing that we know is that the rank of A transpose is equal to the rank of A, which means that the rank of A transpose is also 2, which means that A transpose has 2 pivots. So we have 2 pivots, we have 14 columns, because A transpose is 10 by 14. So 14 minus 2 is equal to 12. So then the nullity of A transpose will equal to 12. That means there will be 12 columns without pivots. So the nullity of A transpose is equal to 12. Now we also want to know what the column space of A is. Well, rank of A equals 2. 2 vectors spans a plane. So that means the column space of A is a plane. But it's a plane in what space? Well, A has 14 rows, so this will be in R14. All right. Now, what is the column space of A transpose a subspace of? Well, it's going to be R10 because A transpose has 10 rows. So column space of A transpose is a subspace of R10. Now, what about the null space of A transpose? Again, we look at the columns for the null space. So the null space of A transpose will be a subspace of R14. Null space of A transpose is a subspace of R14. Okay, so this next question might be, hello, a little bit more complicated because it's not really giving us any information. So this is saying, can a system of the form A transpose X equals 0 have a unique solution? So this actually brings us back to something that we did in the first week of class. I know that A transpose is a 10 by 14 matrix. A transpose is 10 by 14. I don't know why I'm writing in this color. Which means it has 10 rows. It has 10 rows and 14 columns. Now, to have a unique solution, I would need to have a pivot in every column. But because there are 10 rows, the maximum rank, the maximum number of pivots is equal to 10. And what that means is, no, this is not possible because hands down, I am going to have at least 4 columns without a pivot. So here we can say, no, not possible, because of all that stuff that we just set up there. So actually, all of this is important. Okay, now on to your favorite type of question, might, must, cannot. Well, we've only got 2 of them here. We're gonna need to give a brief explanation. So if A is an n by n matrix, so we have a square matrix, and AX equals B has no solution. Well, what does it mean for AX equals B to have no solution? We should always start with the if, ignore everything that comes after, we're starting with the if. What this means is, hands down, there's a column without a pivot. At least 1 column without a pivot. Which means that the rank cannot equal n, because if it equals to n, in order to equal n, this would mean that there are n pivots, which would mean every column has a pivot. Okay, so then if A is a 3 by 3 matrix and the determinant of A is equal to 4, well, this tells me A is invertible because it's not 0. That means A reduces to I. That means A has a pivot in every column. Good. So then the null space, well, if there's a pivot in every column, that tells me that there are no free variables. And if there are no free variables, that means the nullity of A is equal to 0, which means that the null space actually must be a point in R3, because a point is what happens when we have no free variables, when we have a unique solution, or when we have a nullity of 0. Because remember, nullity is the number of vectors in a basis for the null space, also known as the number of free variables. Okay, a couple more. Let A be this matrix without calculating the null space. So I don't want a basis for the null space. I just want to determine if that vector is in there. Well, this is really straightforward. It's yes if AV is equal to the 0 vector, otherwise no. So here I'm just going to do AV, 2, 3, 0, 1, 2. V is 1, negative 2, 1. Oh, hello. Sorry, guys. V is 1, negative 2, 1. Let's get back to that. 1, negative 2, 1. So when I do this multiplication, I get 1 minus 4 plus 3, and guess what? That's 0. 0 minus 2 plus 2, that's 0. So yes, V is in the null space of A. Okay, for 5A, let A be a 5 by n matrix. In this case, we're actually not given the number of columns, but we are assuming that AX equals 0 has only the trivial solution. What that means is A is invertible. A has a pivot in every column, which means that rank A should be equal to the number of columns. So if I have the dimension of the column space is equal to 2, well, remember the dimension of the column space is the same thing as rank. So my rank is 2. This just means n has to be 2. Because it's invertible, there's a pivot in every column, and we have 2 pivots. If rank A equals to 5, what is the column space of A transpose? Well, if rank A is 5, then this means that the rank of A transpose is also 5. I also know that A transpose is an n by 5 matrix. So I have 5 vectors in R5. So, I'm sorry, 5 vectors in R5, because if the rank of A is equal to 5, again, this would tell me that there are 5 columns. A transpose is n by 5, which in this case will be 5 by 5, which means the column space of A transpose is a subspace of R5, but 5 vectors in R5 spans R5. So the answer here is that the column space of A transpose is R5. Okay, now this last one's really gonna make you think. So state true or false. Is it possible for the null space of A transpose to be a plane through the origin? So what this is saying, for the null space of A transpose to be a plane through the origin, this would mean that A transpose has 2 free variables. Now I remind you, A transpose is n by 5. So this would be fine. So yes, it's possible to have 2 free variables if there are 3 pivots. to have two free variables if there are three pivots, because that would be 3 columns left over after the two free variables. That would have to be pivots, 3 pivots. But if there are 3 pivots, then this means that the rank of a transpose is equal to 3, and that the rank of A is equal to 3. So the answer is yes if n equals 3. And then on to our last question here. The graph of the system below is a graph of a system of 3 linear equations. So that means 3 planes in 3 unknowns. So I'm sorry, 3 linear equations in 3 unknowns. So that means 3 planes of the form AX equals B. Determine the dimension of the null space. Well, we know that the null space has the same dimension as the solution to AX equals B. It's just a point different. It's just taking the solution to AX equals B and sticking it on top of the origin. So here, AX equals B, the solution to AX equals B is the intersection of planes which we can see is a line. And we know that the null space, as I just said, is just the solution set to AX equals B, but like transferred, shifted to pass through the origin. To pass through the origin, which means that because this is a line, the dimension would be 2. So my nullity, the dimension of my null space is nullity. So in this case, I'm sorry, did I say 2? I meant 1. The nullity is equal to 1 because the intersection is a line and the dimension of a line is 1. Section is a line and the dimension of a line is 1. And that's my final answer. And that was lab 6. Hopefully it made you think, but also helped you to understand some of these concepts a little more deeply. That's all. Bye.